How and where to use the distributions. How and where to use the distributions. So till now we have learned about the basics of what a random variable is, what a PDF is, and what a CDF is. Correct? So we also learned about a very popular distribution called Gaussian distributions. Gaussian distribution. And we learned the properties of the Gaussian distributions like 68, 95, 99.9 rule. We understood the theory. All this theory is great. Now the big question here is how to use and where to use these distributions. These are two very important questions. So let me give you some examples on how, where, and when to use these distributions. So in a nutshell, all the probability, all the concepts in probability, including that we learn, are mostly used for data analysis. Basically, all those concepts are used for data analysis. Data analysis is all about answering questions about data. So what is this data analysis? It's all about answering questions about data. So all the technique that we learn in probability are used for exploratory data analysis. Exploratory data analysis. This is called exploratory data analysis. Fine. And the exploratory data analysis that we do with probability is all about answering questions about data. Let us understand this a little more with an example. Imagine you are working at a large company, and let's suppose the name of the company is ABC. And let's suppose your task is to order t-shirts. So what is your task? Your task is to order t-shirts. So your task is to order t-shirts for all employees, let's suppose for some annual event, right? Now the big question here is there are multiple sizes of t-shirts. Here order t-shirts for all employees. We know that there are multiple sizes of t-shirts. So we have, let's suppose we have a small, we have medium, we have large, and we have extra large size of t-shirts. And let's assume we have, let's suppose 100,000, 100K or 100,000 employees in that company. So how many Excel t-shirts do you order? This is my question. How many Excel t-shirt you order? And you want everybody to get a right size t-shirt, right? This is my problem statement. If you do not order the right quantity of t-shirts in terms of size, there will be many people who won't get the appropriate size t-shirts, and hence they won't use it. And if you order too many t-shirts of same size, again most of them will go waste. Fine. So it's a very valid real world problem. Now, when you want to solve this problem, how do you go ahead about it? One way is to ask all the 100,000 employees. So what is my strategy one? My strategy one is to collect data for all 100K employees. Right? But let's assume the cost of collecting the data is too high. Then you come up with an idea that typically people whose height are taller than 180 centimeter. Let's suppose I come up with the ideas that the people whose height are greater than equal to 180 centimeters tends to wear a XL size t-shirts. Let's assume that you know this from the common sense, or it's a sort of like some common sense or a domain knowledge, or you have asked people who have done this before. And let's suppose if the height is between 160 centimeter and 180 centimeter, people tend to wear large sized t-shirts. Large size t-shirts. Correct. This is not perfect because there could be somebody who is wider and things like that. But roughly this is logical. Again, this is my domain knowledge. So let me write this. This is my domain knowledge. Correct. Again, this is my domain knowledge that I have obtained from people who have done this before, or just observation about human sizes, or you can say about how the apparel manufacturers manufacture their t-shirts and stuff like that. Since collecting data for all the 100K employees is quite expensive, you would say, let us use this domain knowledge smartly. The way we use it is that we will collect heights of 500 random people. We will collect heights of 500 random people. Since collecting data from all the 100,000 employees is quite expensive, is very expensive. So you'd say, let us use this domain knowledge smartly. The way we use it is that we'll collect height of 500 random employees. Correct. Let us say I try to do this. So I have 500 heights here. So from these 500 heights, what I will do, I will try to estimate the mean and standard deviations. So I will try to estimate the mean and standard deviation. Correct. This mean and the standard deviation is actually a sample mean and a sample standard deviation. It is not the population mean and population standard deviation. So my first assumption is that we can determine the size of t-shirts from the height of the people. This is my first assumption that we have taken, which is a reasonable thing. And since I cannot collect height of 100,000 employees, I'm saying let us take the height of 500 random samples. So this is my 500 random samples. So how you are going to collect the height of 500 random employees? So let us say at the gate of entry to the office, we randomly filter 500 people and say, could you just give me your height? It will not take more than, let's say, 10 seconds to measure it. So you got the 500 values. Now from these 500 values, you got the mean and the standard deviation. Of course, these are sample mean and sample standard deviation. My sample mean and standard deviation are roughly close to my population mean and population standard deviation. It is an approximation actually. Somebody tells me that the heights are, this is my heights are normally distributed with some mean and standard deviation. And I already computed my mean and standard deviation. I know that heights are Gaussian distributed. Again, who told me this? It is probably a doctor or a physiologist who knows that typically the distributions of heights are normal. And I approximated the population mean and standard deviation using the sample mean and sample standard deviation. Now, given this, I can answer lots of questions. So what is my original question? My original question was, how many XL size t-shirts should I order? And if I know the sample mean and sample standard deviation, I can easily compute the probability of my height greater than equal to 180 centimeters. Fine. Because the moment I know the distribution, I know the mean and I know the standard deviation, I can now plot my PDF and my CDF. So let us plot the PDF and CDF. So if I'm going to plot my PDF, let's see how my PDF will look like. Now in my CDF, let us assume that these are my heights. So now I will say where is 180 centimeter. So let's suppose mark this. Let's suppose this is my 180 centimeter. Here I am marking this as 180 centimeter. Yeah, let's suppose this is a point where this is my 180 centimeter. Fine. I can read this from my CDF, because what will my CDF look like? If I, let's suppose, look at my CDF of my, this is my Gaussian distribution. And if I look at the CDF of my Gaussian distribution, the CDF look like this. The CDF will look like this. Just the fact that the heights are normally distributed, if I know the mean and the standard deviation, and I can plot the CDF, correct? So these are my heights of the CDF, and this is corresponding to my 180 centimeter. This is corresponding to my 180 centimeter, and corresponding to this 180 centimeter, let's suppose this CDF is like 99%. Corresponding to this 180 centimeter, let's assume this CDF is 99%. Correct? These are my heights, and this is corresponding to 180 centimeter, and corresponding to this 180 centimeter, let us assume the CDF value is my 99%. Then I know that the probability of height greater than equal to, let's suppose, 180 centimeter is 1%, which now means that of the 100K employees, 1% is taller, 1% of the employee is taller than 180 centimeter, which means 1% of the employees would need an XL size t-shirts. So I will order roughly 1% of this. So 1% of this is roughly 1000, 1K. So I will order 1K t-shirt as XL t-shirt, which means 1% of the employees would need an XL size t-shirt. So I will order roughly 1% of this, which is 1000 t-shirt. Now, here we have done lots of assumptions and lots of analysis. My first assumption is that we can predict the size of t-shirts. We can predict the size of t-shirts based on the height, which is a reasonable, commonsensical thing. Next, we have assumed that height is a Gaussian distributed random variable, and I am computing the mean and standard deviation using a sample. The fact that the heights are Gaussian distributed will help me get a CDF and all the values in it. Right? So in a nutshell, the very fact that the heights are Gaussian distributed or normal distributed, I can use a theoretical model on the distribution of height itself. Heights are Gaussian distributed, give us a theoretical model. So in a nutshell, the very fact that the heights are Gaussian distributed give us a theoretical model on the distribution of heights itself. I can simply plot this CDF, correct? The moment I know the mean and the standard deviation. Why this is a theoretical model? Because this is observed in many natural phenomena. Observed in many natural phenomena. Correct? But the distribution itself is a theoretical model. And the moment I know something about Gaussian distributed, I can make all of these observations and I can answer all of these very, very important questions that we are dealing here. So this is a very real world data analysis questions. Probably a lot of people in the, let's say, HR team who have to order t-shirts would actually use data like this. Similarly, let us take a slightly different example where distributions are useful. So let us take a second question. Now let us assume I have salaries of all the employees in a company. And now the first question is, if salaries are Gaussian distributed with some mean and standard deviation, I can answer questions like how many employees make a salary, let's suppose, greater than equal to $100,000. Correct? So if salaries are Gaussian distributed, I can answer questions like how many employees make a salary greater than equal to $100,000. If I know the distribution, so this is a big if here. Why this is a big if? If your salary is, let's suppose, as if this salary is Gaussian distributed with some mean and variance. There are three parts here. First part is that this is Gaussian distributed and I know the mean and the standard deviation. And as soon as I know this, I can take all of the theoretical model of what a Gaussian distribution is, and I can answer questions like this. How many employees make a salary, let's suppose, between $50,000 and $70,000? So I can answer how many employees make a salary between $50,000 to $70,000. Correct? I can again read this from the CDF, right? So let me draw CDF for you to make you more understandable. So I have plotted the CDF. So imagine if this is my CDF and this is, let's suppose, $50,000 and this is $70,000 and this is a value, let us say this is 0.4 corresponding to $50,000 and this is the value, let's say 0.7 corresponding to $70,000. I know that about 30% of my points lie between $50,000 and $70,000. This is the CDF of salaries, right? I know that 40% of my points lie below $50,000 and 70% of my points lie below $70,000. So there are 30% of people are employees who make a salary between $50,000 and $70,000. All of these are very important data analysis questions. All of this is a part of data analysis and you can answer that if I know these salaries are Gaussian distributed and if you can estimate the mean and standard deviation. Now, the big question here is, how do you determine this? The first question is, of course, you can use sample mean and sample standard deviation and all of that. But how do you test that your salary is a normal distributed or not? So this is where we already have discussed this earlier, where QQ plot comes into picture. We have already learned this QQ plot in the previous sessions. Those of you who want to learn, you can check the statistics of AI playlist episode number 9. Imagine if I have, let's say, salaries of 1,000 employees or 1,000 observations, right? So if I have, let's say, salaries of 1,000 employees or observations, I can use the QQ plot to determine if actually salaries are Gaussian distributed or not. Later, we will learn other techniques like KS test to determine if salaries are Gaussian distributed or not. If salaries are not Gaussian distributed, we can't use CDF. We can't use CDF. Correct? If salaries are Gaussian distributed, then and only then we can use CDF. So Gaussian distribution is giving us a theoretical model of the distribution of data, and Gaussian distribution is observed in lots of cases in natural phenomena. There are many other distributions that we will learn little later in this course, but each of these distributions literally provide us a theoretical model on the distribution of data that we can see from the PDF and CDF. This is my PDF and this is my, let's suppose, CDF, and this is my CDF. My CDF will look like this. So this is the PDF and this is the CDF. The PDFs and CDFs of a random variable X tells us how data is distributed. Imagine if I'm observing the same type of PDF and the same type of CDF in many things. It makes sense to build a theoretical model which I can reuse multiple times. And if I can find some other data to be belonging to Gaussian distribution, I can use the learnings that I have from the theoretical models like 68, 95, 99.7 rule. We got this rule for the Gaussian distribution. And if you can tell me that any random variable is now Gaussian distributed, I can use the same rule here. So distributions, especially these distributions, are Gaussian distributions. So distributions, especially Gaussian distributions, are theoretical models of what to expect. What are the properties that this random variable would have if it is following the theoretical model. But of course, it also has applications in data analysis, like the couple of stuffs that we have seen before. So thanks for coming. So I will see you in the next lecture.